Copy. This, continuing on from where we left off. So, we said the problem, Mitchell, that we have to deal with, and unfortunately it's going to be a hefty calculator problem, is I cannot use MGH. Why couldn't I use MGH for potential energy anymore? You guys spotted it last class pretty quickly. What's the problem? G is changing. So we said if I treat it like the area under a graph, we were able to derive this equation. Big G, big M, little m over R. Now, by the way, this is gravity. This is potential energy. Is it possible for people to get them mixed up? Yeah, don't, is all I can say. We got this equation, and then we added the negative. Why negative? We have defined zero energy out at infinity. We've said if you're out at infinity, you won't fall. That means you have no energy. If you're closer than infinity, you will fall back down to the Earth. And, you have to add energy to get to zero. That means you must start out with negative energy so that you can add energy to get to zero. And we looked at... we said how fast, change in height, change in speed, curvy. I did conservation of energy, but I had to use the cosmic energy. Example 2. This is the third longest question of the year. We'll also get to the second longest and the longest today. Example 2. Everybody got it? Okay. Mitchell, what's example 2 asking me to find? How much what? You're right. Work. Mitchell, don't write this down. Why can't I go, the work is going to be the force times the distance? Where this force is gravity. It's changing. The further I go from Earth, the weaker gravity's getting. Yeah. This equation only worked for a constant force. Work was also the area under a force versus distance graph. Mitchell, do you see a graph anywhere in this question? So, for all the money, do you guys remember the third and most useful and flexible definition of work? I'll give you a hint. It had some change-ins in it. Write this down. We're going to start with the simplest case, Mitchell, and then we're going to build up. What word did I boldface and underline in the typing? All we're doing is we're going to launch a rocket straight up, not put it in orbit, so it's going to come crashing straight back down. Okay? At the top, for a split second, Mitchell, how fast will it be traveling? I'm going to ask you the same question. I'm just going to phrase it differently. At the top, for a split second, how much kinetic energy will it have? 0. Before we launch it, how much kinetic energy does it have before we actually start the engine? In other words, what's my change in kinetic energy if I'm just lifting it up? Okay, so you can make a little note here. Because we're doing that, VI and VF are 0, so I can do that. By the way, to put it in orbit, then I'll have to add the kinetic energy required to give it just the right sideways. You know what? To give it the V orb, the square root of big G, big M over R. That. Yeah?
Would it actually come crashing down?
We're going to... Okay. I think I know where you're going, so I'm going to cut you off just for a second because I think I'm going to be dealing with this in a question, but I'm going to say, in our simplest case, let's pretend the Earth isn't rotating and everything is standing still right now first. Okay? And I know, and actually it leads to some good physics. You wanted us to be moving? Is that what you're going to say? No, not yet. But we'll deal with that later. Hey, Mitch, what's changed in anything? Okay. All of you, by the way, want to get out your calculators, and I'm going to try and show you some good calculator shortcuts. Don't write this next bit down. Mitchell, why can't I go like this? Well, I got it, little g is changing, right? Okay, so we have to use our, in other words, what I usually ask now, I'll phrase it this way, Mitchell, are we cosmic? Are we in space? Then I better use the space, the cosmic potential energy. Negative big G, big M, little m over R final, write this down, minus negative big G, big M, little m over R initial. Oh, do you notice anything kind of nice? The masses don't cancel because there isn't a mass in work. And they shouldn't. It should actually be way tougher to move the space shuttle up there than to move a little tiny satellite up there. Right? What? Oh, that's Manny? Sorry. The minus minus is up? Okay, let's keep that in mind. I agree, by the way, the minus minus is going to become a plus. Okay? Manny, let's plug and chug. There's going to be a negative. What's big G? What's big M? The planet, and since it doesn't, yeah, Earth, 5.98, yes? Times 10 to the 24th. What's little m? 1200? Over. What's our final radius? Well, we got to be careful. Mitchell, this question gave me a height. What this question has given me is that this distance here, the height, is 1.2 times 10 to the 7th. But what I want, Manny, is this distance here, the radius. How could I get that? Okay, so in the bottom of this fraction, I'm going to go like this. R Earth, which is 6.3, it's on your sheet, right? Plus 1.2 times 10 to the 7th. Kohei, you okay with all that? Oh, you're having to borrow off Manny? Okay. By the way, there is room up here if you need to get closer. I was looking at the, oh, okay. Manny, what did you say about that minus minus? So it becomes a? Okay. And here's, by the way, I don't know if you guys are in my situation. I'm more than halfway across the page and I'm worried about space, but just watch. Manny, what's big G? Wait a minute, Manny, is that the same as this number right here? Ditto mark times. Manny, what's big M? Really, same number as here? Ditto mark times. What's little m? Really the same? I'm going to put another ditto mark right there, and I will allow you to do this, partly because it just becomes increasingly tough to fit all this on one line. Okay? All over. What's going to be on the bottom? Not ditto mark this time, otherwise they just, everything would be, answer would be 0. That's what you call it. It's called a ditto mark, right? Well, you learned a new word. 2 words. Sorry, what? Okay. Now, it seems to me, Jason, with a bit of cleverness, since I'm repeating numbers in my handwriting, maybe I can cleverly repeat stuff on my good calculator as well. I have one student in my block A who has the most POS calculator, and this is where he's realizing, because he is stubbornly stuck with one that doesn't have backspacing and arrows, it only has one line. It's one of those ones that when you press brackets, the screen just flickers, and that's how you're supposed to know that you've added a bracket. It can't show brackets. He's stuck with it, and yesterday during the lesson, I just saw him quietly start to cry. No, he didn't, but I saw him going, oh. So you ready? You got your calculators out? Here's how I'm going to type this. I'm going to very, 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 very carefully type in the first expression. So negative 6.67 scientific notation negative 11 times 5.98 scientific notation 24 times 1200. And I usually pause here. I double check because I want to make darn sure I get this right because I'm going to be repeating it for the second one. So far, so good, Clay? divided by, Clay, is there more than one thing in the bottom? I'll put it in brackets. Radius of the Earth, Dale, you just looked it up, didn't you? Is it 6.38 times 10 to the 6th? Good. I usually memorize it in this unit, and I forget it again in a few weeks. Oh, and then plus 1.2, scientific notation button, 7. And I hit equals. Little rule of thumb, you're going to find the amount of energy to put something in space will almost always be a 10 to the 10th or a 10 to the 9th if I'm making up reasonable numbers, and I usually will be. In other words, if you get an answer like 10 to the 5th, you've screwed up. If you get an answer like 10 to the 20th, this isn't Star Trek. Okay? You're going halfway across the galaxy. I'm going to carry a bunch of, I'm going to go negative 2.60413 times 10 to the 10th. Negative 2.60413. Manny, what did you say the minus was? A plus. And here is where my care in the first entry, Mitchell, bails me out. Hopefully all of you are able now to backspace. This is why I went on that rant. By the way, it was this unit. This is why I went on that rant about calculators at the beginning of the year. You can on yours. Try going left arrow. Yeah. Does it work?
And you go back and edit it?
First of all, has it now brought up the previous line? Yeah. So now you go back and edit it with your arrow keys.
Oh, that's
Delete the negative sign because you told me the minus becomes a plus. Yes? And then, Manny, what else do I need to change? No, actually, sorry, Jason, you were the one that what else do I need to change? And again, this is why hopefully you've learned where your delete key is. I'm telling you, not only is that faster, it way cuts down on the likelihood of you making a typo. You type the first one in very, 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 very carefully, and then you repeat most of it for the second one. And that will always work because you're always going to be starting and orbiting the same planet. Like, I'm not going to have you start on one planet and end up on a different planet and have to change the masses. Your satellite mass isn't magically going to change all of a sudden. Okay. Should get a positive answer, yes, because I deleted the negative. Now, if you forget to delete the negative and you just get a negative answer, it's pretty easy to write down the positive version. Anyway, I get, hey, it's in the 10 to the 10th range. Yay. I get 7.50218 times 10 to the 10th. Mitchell, we're going to come all the way back to you. You told me that change in anything was final minus initial, which I've done. It did become a minus, which is a plus. So I think all I want to do is add these together. Yes? Oh, but Mitchell, don't I already have this number stored on my calculator? So really all I need to do is take away this. Take away 2.60413 times 10 to the 10th. How many joules of energy will it take just to fire this rocket straight up? That much. Now I'll go to 3 sig figs. I guess 4.90 times 10 to the 10th. Did you all follow what we did there? It's a much nicer way. I used to actually type all these in, and about 6 years ago I clued in, oh, wait a minute, let's backspace. I get 4.89. If I go to 3 sig figs, I'm going to round there. The 9 is going to become a 0. That 8 is going to become a 9. 4.90 times 10 to the 10th. Mitchell, units, it's work. Joules. Okay. Haven't forgotten your question. We're going to get to it in a second, but just patience. So, everybody get that okay? Sadly, that's not the longest question. Not even close. But here's what I wrote here. Since the satellite has no kinetic energy, it's going to come straight back down to the Earth. To lift an object, we only need to give it... To put an object in orbit, we still need to give it potential energy, but we also need to give it kinetic energy. Okay? So now, let's do some rocket science. And by the way, when I'm asking how much work, really what we're saying is how much fuel would you need? We'd need to know how many joules per liter of energy we got from the rocket fuel, but that'd be simple to look up. This is, if you're wondering why it's so expensive to put stuff into outer space, because we're to keep getting 10 to the 10ths and really big numbers. It's a lot of energy. Example 2. Clay, what does example 2 want me to find?
How much work is done?
Why can't I go force times distance?
It's probably
I could also find the area under there's no, we're going to go to our best definition of work. Work is going to be the change in potential plus the change in kinetic. Clay, will the change in kinetic be 0 this time? There, you know what? There's an orbital speed. Now, I actually, Trav, calculated the orbital speed with that radius. I crunched the numbers. The next step would be, what if I just gave you the radius and actually didn't give you this speed? Well, then you'd have to go, gravity is what's pulling me in a circle. And you can find the speed as well. That's the longest question. The longest question of the year, you calculate the change in potential, you calculate the change in kinetic, but you got to find the speed on your own as well. Okay? I bet you that's the next one. I found, Clay, because none of these is 0, I don't do them all at once. I do them one at a time. Pick, do you want me to find change in potential or change in kinetic first? Doesn't matter.
changing kinetic.
Change in kinetic. Okay. I usually do that. And I say, Clay, what's change in anything?
Final mass movement.
And kinetic energy hasn't changed since physics 11 as an equation. What's the equation for kinetic energy? Ke equals a half. So this is going to be a half mv final squared minus a half mv initial squared. And now I can answer Josh's question. Josh, we're going to assume worst case scenario. We're going to assume that you're starting at rest, just because the math gets yucky otherwise. You're not starting at rest, though. In real life, the Earth is rotating, and you're on the Earth. Where are you rotating the fastest? The equator. The further south you can launch from, the more of a natural boost you actually get from the Earth. This is why the U.S. built Cape Canaveral in Florida and Houston as far south as they could. It's also why they always launch to the east. They're launching both over the ocean for safety, so if something goes wrong, stuff will go in the ocean, but they're launching with the direction of the rotation of the Earth. This is why the Russians had such a tough time with their space program. Further north, they couldn't take advantage of as much kinetic energy from the Earth. This is why, even to this day, the Russian rocket engines are workhorses, because they had to engineer them that way. They are just these really powerful suckers. They're simple, they work, and boy, do they put out wattage or horsepower or however you want to manage power. Elon Musk is attempting to learn how to land on a ship, because what he wants to do is launch and land from a ship. Where would be a clever place to put that ship? On the equator. Then you get the best bang for your buck. Where would the worst place to launch from be? So this is going to be Santa's NASA. Okay? That's what you were kind of wondering about, and it's true. The problem is then I'd have to tell you what longitude or what latitude we were at. We'd have to crunch how fast the Earth was moving at that point. I'm not going to go down that black hole. So this is going to be worst case scenario. Clay, we're going to assume we're starting at rest, even though technically we're not. Oh, this isn't too bad. Clay, did they tell me the mass?
Yep.
Which mass, Earth or satellite? What's moving? What's in orbit?
Satellite.
Okay, so 925. Did they tell me the orbital speed? What?
3,913.
Don't forget the squared. I've told you, by the way, you'll find you get 10 to the 9ths and 10 to the 10ths here quite often. If I'm making up reasonable numbers, that's your built-in error check. In other words, if you don't, you probably forgot the squared, right? And I get 7.096, I'll make that a 1, times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. Some of your calculators might already give this to you in scientific notation. I've got a 10-digit display. 7.0961. 7.0961 times 10 to the 9th joules. That's how much fuel I better pack just to keep my satellite in orbit, to give it the right orbital speed. What else do we need to find? Sorry, by the way, I put a W here. I should have put a change in kinetic here. Yep. The other thing I usually do, because this is a long question, once I find one of these, I tend to put a box around it just so I can find it easier on my page later on. What else do I need to find, Clay? I got to be fussy. You said potential energy. I have to slightly disagree with you because that's not quite what I wrote. Change in potential energy. I'll do that in blue. Clay, what's change in anything? What's change in anything? What's change in anything? Are we cosmic? Are we in orbit? Are we in space? Then I better use the cosmic potential energy. It's going to be negative big G, big M, little m over R final, because that's the final potential energy, minus negative big G, big M, little m over R initial. Manny, what do you notice? Going to be a plus on the next line, which, by the way, is nice because even though we've defined 0 to be infinity, and even though we've said we're negative, you'll notice we do get the signs take care of themselves, and we get positive answers, which we should, because when you have to add fuel, you're not getting free energy out of this. Okay, Clay, you ready? Oh, don't forget the negative. What's big G?
6.67.
Yep.
Times 10 to the
Negative 11.
11.
Big M. Big M.
5.98 times 10 to the 24.
Little m. Was it 925?
Yep.
All over. Did the question give me an altitude or a radius? Kyle? Oh, so I don't need to add the radius of the Earth this time. I can just write that number down. What is the radius, Clay?
2.6 times 10 to the 7.
That's where we're ending up. Plus, minus is a plus. Oh, Kyle, what do I call this thing? A ditto mark, and a ditto mark, and a ditto mark. In other words, the top isn't going to change.
Did you just put one ditto? Did you just representing the whole thing again with one ditto?
I'm not going to be fussy. This is just me wanting to make sure that I walk through every step. Yes? Not enough to worry about. I think it's less than 0.1% because the Earth does bulge at the equator slightly, but not enough to worry about. Hey, speaking of, what's my initial radius? Where am I starting? Surface of the Earth, which is what? Okay. I'll tell you by far the most common mistakes I see on, by the way, I like this question, is I see kids with all the right numbers and then they write down the wrong answer. It's calculator errors, which is why I've been yelling at you so much the last couple of days about try this on your calculator. I'm going to do this without saying anything. See if you can get the same thing as me. Double check. See if you can get what I got.
Can you go back into your equation?
The TI's second function, enter. Okay, and I think the TI's remember your last 20 lines. If you don't, but if you go second function, enter again, it'll go 2 lines ago. Second function, enter, it'll go 3 lines ago. And so it remembers quite a bit. In fact, to be honest, what I would have done, because I actually know that I had typed that number and that number in the previous question, I would have actually gone all the way back to my previous question, deleted the mass, changed it, deleted the radius. I'm that lazy, and I just know, oh, I got it on there. I'm sure somewhere if I go back a few lines, there's a 6.67 times 10 to the negative 11 and a mass of the Earth, because we're sticking local.
Yeah.
I got, do you guys get 4.3639 times 10 to the 10th? Okay, and I'm keeping the extra sig figs, Dustin, so that when I add stuff together and round off, I'll be good to 3 sig figs. Who has the built-in constants on their calculator? So you're going to find by your 4th or 5th decimal, 4th or 5th sig fig, your answer will be different from mine, but we should still be good to 3 sig figs at the very end. You just might notice along the way some of your numbers look a little different. We're not done. Clay, what did this question want me to find? No.
How much work?
How much work? And what did you say work was equal to? The change in plus the change in? Well, here's the change in kinetic. Here's the change in potential. I guess now, got to add them together. The work is going to be 7.0961 times 10 to the 9th plus 4.3639 times 10 to the 10th. Conveniently, I have the 4.3639 still on my calculator. If I want to put this satellite in orbit, that's how many joules of energy I need to give it. That would tell me how much rocket fuel I need. Sadly, that's only for the satellite. That doesn't even include getting the rocket itself that's carrying the satellite up there. So it's rocket science. 5.07 times 10 to the 10th, yeah? And I would take 5.06, 5.08. In fact, I'd take 5.1, really. But more than that, I'd be a little frowny. It means you probably take 5.07 times 10 to the 10th joules. Whew. Okay. So there's 2 main ideas, Vikas. How much work just lifting it up? If I just lift it up and I don't put it in orbit, what's your change in kinetic energy? 0. If I want to put it in orbit, it's going to be change in potential plus change in kinetic. All right. Let's do a little thought experiment. Let's suppose we're going to launch a missile or a rocket from the surface of the Earth, but we're going to use all of its fuel up in one mighty burst all at once. In other words, it hits full speed right away and doesn't accelerate anymore. This is just to keep the math simple. So the only force it experiences as it rises is gravity. Let's even ignore air resistance. As it rises, what happens to its kinetic energy and what happened to its orbital energy? So there's a little picture. What would happen to the kinetic energy as it moved away from the Earth? Well, really, what would happen to its speed as it moved away from the Earth if we weren't running the engine? It's going to slow down because Earth is tugging it down. Yes? So if its speed is getting smaller, I think that means its kinetic energy is also decreasing because of half mv squared. What's happening to its potential energy? Isn't that the law of conservation of energy? If kinetic goes down, that energy's got to go somewhere. Oh, it's going into potential, which is getting bigger. Okay? So it seems to me, with a bit of cleverness, we might be able to fire our engines once in one mighty burst, boom, and shut them off and keep coasting all the way to the edge of the universe and time it just so that right when we're slowing down, right when we get to the edge of the universe, we come to a stop.
Or we never would.
Absolutely it would. In fact, we have a name for it. We call it escape velocity.
You would never be able to get to the end of the Earth or the end of the universe. It would
No,
be
but you can
expected
get
to
out,
happen.
you can get a velocity such that the gravitational field of the planet that you're leaving has lost you. Now, you're not going to fall back down anymore. Anything faster than that would mean not only you're not going to fall back down, you'll have some velocity left over to keep going. This is escape velocity. Really what escape velocity asks, Clay, is how much work is necessary to bring potential energy to zero, which for us is relative to zero at infinity. Clay, you're right. Instead of infinity, let's say a really long distance away. Okay, there's our compromise. We can solve for an escape velocity using conservation of energy. Because it seems to me, if you fire your rocket all at once and then let it coast, is there a change in height? Yeah. Is there a change in speed? Yeah. Is there a yucky, curvy path? Well, believe it or not, gravity is warping the curvature of space-time. Yeah, gravity is changing. Yeah. So you ready? So again, here's my analogy. I want to fire, here's the Earth, I want to fire my rocket once, boom, and then coast, and I want to do it so perfectly that I come to a stop out at infinity. Did I say come to a stop? What's my final speed going to be? What's my final kinetic energy going to be? Hang on a sec, Clay. Where do I want to come to a stop? Out at infinity. Out at infinity, what have we defined my potential energy to be out at infinity? In fact, what I really have is this. KE initial plus PE initial equals 0. Now this looks a little weird, but let's go with it. Are we cosmic here? Yeah? Then let's use the cosmic potential energy. KE is still a half mv squared, but it's going to be plus negative big G, big M, little m over R initial. That equals 0. Oh! If I wanted to make this equation prettier, what might I do with that negative big G, big M, little m over R initial? Why don't I add it to the other side? Because there's a 0 there. So really what I get is this. A half mv initial squared equals, now it's positive, big G, big M, little m over R initial. Oh! I just noticed something else. Turns out escape velocity, doesn't matter whether you're the space shuttle or a tiny satellite, that velocity is going to be the same. It's going to take more energy, more fuel to get you to that escape velocity if you're bigger. True. But the speed is going to be the same. I guess I want to get the V initial by itself. How fast do I need to leave the Earth at? How would I get the V initial by itself? What will I do with that 1/2? I could divide by a half, but what's a nicer way to get rid of a 1/2 on one side? Okay, let's cross this out. Let's put a 2 there. That gives me VI squared. This is the equation for escape velocity. The escape velocity from any planet is going to be the square root of 2 times big G times big M over whatever the radius of the planet, wherever you're starting. That's kind of, first of all, I love the fact that it's such a clean equation. It looks a little bit like orbital speed, but the 2 is there and it's your initial radius. But that is how fast you would need to leave in order to escape the Earth's gravitational pull or the moon's gravitational pull or the sun's gravitational pull. And we have done that. It's how we went to the moon. They went far enough that eventually they could shut their rocket engines off and coast the rest of the way. Also, it was helped by the fact that the moon has enough gravity that was also pulling it in, so there was also a force in, but there was a point about 2/3 of the way away from the Earth towards the moon where the joke was, we've just put Newton in the driver's seat, we're coasting now. Hey, what is the escape velocity of the Earth, I wonder? Oh, and the moon. Okay, let's do the Earth right here. Let's do the moon right here. So escape velocity is 2 big G, big M over R. Square root of 2 big G is 6.67 times 10 to the negative 11. Mass of the Earth is 5.98 times 10 to the 24th. I didn't leave myself much room here, Mr. Dewick. Our initial, let's assume we're launching from the surface of the Earth, as opposed to launching from somewhere in orbit, like from a space station or something like, let's just launch from the surface. So 6.38 times 10 to the 6th. Times 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th divided by 6.38 times 10 to the 6th. That's too big. Oh, square root. You actually get a pretty nice number. It's just past 11,000 meters per second. 11.2 thousand meters per second. 11.2 kilometers a second. I'm going to write 1.12 times 10 to the 4th meters per second. We've done that. The New Horizons, the one that went to Pluto, went much faster than that, as a matter of fact. They're still talking about, and it would be kind of cool if it happened in your lifetime, building a moon base. It'd be way easier to launch stuff from the moon because you have a smaller gravity. What would the escape velocity from the moon be? If it's okay with you, Dustin, I'm not going to rewrite the equation. I'm just going to plug in the numbers. So it's going to be big square root of 2 times 6.67 times 10 to the negative 11. What's the mass of the moon? I have no idea, but I know it's on your sheet. I just know it's smaller than the Earth. 7.35 times 10 to the 22 divided by, and let's leave the surface of the moon. What's the radius of the moon?
1.74 times 10 to the 6th.
Nick? Second function enter, second function enter brings me to this line, and I've got the 2 and I've got the 6.67 already sitting there. I'm only going to retype the second part. 7.35 times 10 to the 22 divided by, oh, decimal didn't go, Mr. Duke, 0.35 times 10 to the 22 divided by 1.74. Oh, the 10 to the 6 is already sitting there. That's kind of convenient. Square root of that. That's easy. 2,370? That's quite doable. In fact, that's doable probably without actually using like rocket engines. Maybe you could do that launching it using an electromagnetic motor or something. Oh, that opens up some other options. Okay. Last one. An 1,800 kilogram satellite is placed in a stable orbit with a speed of 4,200 meters per second. A says, find the orbital radius, and B says, find how much work is required. I would have no problem, Spencer, just asking you, well, how much work is required, and you would say, blah, 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 change the potential. I need R. And in other words, I have no problem asking you to clue in that you have to do A first, no matter whether I ask for it or not. Spencer, what does A want me to find? What kind of radius? Gravity is what's pulling me in a circle. There's my trigger. Yeah, I'm going to work sideways, I think. Big G, big M, little m over r squared equals m. Which version of a circular acceleration do I want to use, Spencer? The one with the V or the one with the T?
The one with the T.
But sorry, the one with the...
V.
Yeah.
Oh, okay. V squared over r. For orbits, the mass cancels, not for how much work to put it up there, but once you're up there, the mass cancels. What do they want me to find in part A?
Orbital radius.
You know what? I think this r cancels that r. How would I get the... You know what? I think this r will move to the top. Yes? And the v squared will move to the bottom. I've just derived yet another equation, which is why I said don't bother memorizing every equation out there. It looks to me as though the orbital radius is going to end up being big G, big M over V squared. It looks to me like the orbital radius is going to be 6.67 times 10 to the negative 11. Big M, mass of the Earth. It is Earth. Well, it doesn't say a different planet, so I'll assume Earth. Divided by 4,200 squared. And I get an orbital radius of that 2 point, I'll carry some extra sig. You know what? I'm going to write this out and then I'll round it off because I think for the work part I want to use this anyways. So I'm going to go 2261141, 2261141, which is 2.26 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters. Is that okay, Kev? What's B want me to find? Oh, no, I can't go force times distance. It's also the area under a force. What's my other definition of work?
Negative.
Change in potential
Potential.
plus.
Change in kinetic.
Are any of these zero? Not if we're in orbit. If we were just lifting.
Yeah.
Okay. What do you want to find first?
Kinetic.
Okay. Change in kinetic is going to be a half m v final squared minus a half m v initial squared. And Josh will do worst case scenario and assume vi is 0. Did you have a question? Oh, yeah.
Can we keep that stable order? Because the moon is different, and the point is
Not noticeably. Our,
like do orbit degrade over time.
the low Earth orbits, like the ISS, are actually still scraping against the very, very thin atmosphere at that level. That's what causes it to degrade. But if you're asking me, like the geosynchronous ones, which are way out there, no, they're fine. Yeah, they're there. But also realize we're ignoring every other planet and astronomical body. The moon would also play a role. The sun will also play a role. And we're ignoring that. There are, if you're bored, do a Google search for something called Lagrange Points, Lagrange. I think there's 4 of them. Those are spots where if you add up all the gravitational forces from everything in the solar system, it's 0. That's where you can actually park something and not have it moving. It'll hover there. So that's where they're talking about putting some of the next generation of space telescopes. And as far as we know, those would stay there. But they're way out there. 2 of them are well past the moon, so it would not be like the Hubble where we could service them. Once they're out there, they're there until they burn out, and then once they burn out, we would probably fire a last rocket to push it out of the Lagrange point and have it slowly fall into the sun. Is the big garbage disposal of the solar system, right? Good question. I know I can count on you for those. Little m, 1800, 4200 squared, oh, 10 to the 10th, which is what I said often is, 10 to the 9th, 10 to the 10th. 1.5876 times 10, 1.5876 times 10 to the 10th joules. That's how much work to keep it up there. Kev, what else do we need to find? What's changing anything? Because I'm running out of room, I'm going to skip that, and I'm going to go straight to writing the cosmic potential and negative big G, big M, little m all over our final minus negative big G, big M, little m all over our initial. By the way, Kevin,
Yes.
I would have done this first before that because I could have used my answer button for that. And yes, I'm that lazy and do think that far ahead. Just saying. But that's okay. I wrote it all down. It's not that much typing. Hey, Manny. Knock, knock. 2 minuses equal up. That's right. And by the way, I'm doing that on purpose because every year there's always one kid that forgets that and puts a minus on the second one. And now you get like a negative potential energy and they start freaking out because everything seems wonky. I think I can fit this in. Negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. 1800. Our final was 2261145 2261141 plus we're starting out on the Earth. Whew. Negative 6.6. You know what, Mr. Dewick? Let's see. Ready, Nick? Nope. Oh. No. Oh, yeah. I got a 6.67 and I got an Earth. I can tweak this one here. Do you know how to insert on your calculator? Do you know how to insert? Second function delete. There's the negative. There's the 6.67. There's the mass of the Earth times 1800 divided by 2261141. That first one is negative 3.1752 times 10 to the 10th. Negative 3.175. Yep. Don't forget the plus. Backspace. Nuke the negative. And I guess I got to change the bottom. It's going to be 6.38. Scientific notation button 6. And I guess I got to delete the rest of the stuff there. Yeah. There's that one. 1.1, ooh, 10 to the 11th. We're way up there. 1.1253, 1.1253, that'll work. 1.1253 times 10 to the 11th. Plus negative 3.1752. have, there's the change in potential. I haven't looked. I got a positive answer, didn't I hope. Whew. And it's in the 10 to the 10th or 10 to the 11th or 10 to the 9th range. Whew. I'm pretty sure I'm right. 8.0781 times 10 to the 10th. 8.0781 times 10 to the 10th joules. Now that's the change in potential. Am I done? No. I wanted to figure out how much work. Work is going to be that number, change in potential, plus that number. Change in kinetic. It's going to be this number plus 1.5876 times 10 to the 10th. Holy schmoly. 9.6, for me, that 6 isn't going to stay a 6. It's going to become a 7. 9.67 times 10 to the 10th joules. Is that right? Anybody else get the same as me? No? Yeah? You got the same as me, Raj? Okay. Sorry, Trav, it's rocket science. I mean, what do you want me to do? At least it's not brain surgery. Okay. What's your homework? So we saw the video, how to build a Death Star last day. Number 1, number 2. I have one, but patience. 1, 2, 3. Skip 4, 5. Skip 6. 7. 9 is good. Maybe 10. Let me see. Yeah. Well, 10 is the moon, and I'm a nerd enough that, yay, I get to be on the moon. Yeah. 11 is just a conceptual question. 13 is cool. $14 and $15. I'm sorry, but this is a tough enough concept. I need to throw a lot of practice at you. Now, I wanted to give you 20 minutes. You're going to get 19. Mr. New, I do. You can work, or let me pause this first of all.